according to the clock up there, we're already late. Well, we're 21 seconds late. For those of you who came today to hear a talk by Keith Genreau about the neutron star interior composition explorer, you will be disappointed, as we all were. Keith, unfortunately, had to postpone his trip due to an illness in his family. But when one door closes, another one opens, and our own Shep Doeleman graciously agreed to step in and give what I think will be an equally interesting talk about the Event Horizon Telescope. Well, a little louder? Or Shep got his BA at Reed College in Oregon and then a PhD locally at MIT. And as most of us are aware, Shep is one of the driving forces behind the Event Horizon Telescope, which is a short wavelength, very long baseline interferometer that's designed to image supermassive black holes, most notably the one at the center of our own galaxy and at the center of Virgo A, down to the Schwarzschild radius resolution. Doing so, as Shep will explain, will enable very interesting tests of general relativity and the strong gravity regime, direct magnetic field structures through polarization, and time-resolving black hole orbits. Today, Shep will remind us of where the project stands at the moment. He will hopefully show us the latest results and tease us with some results that we hope to see in the next 2 to 3 years. Thank you, Shep.
Is this on? Yeah. You can hear me? Okay. Well, thank you for the nice introduction. It's nice to give a presentation to the home team, as it were. Oddly, Keith Genreau, the speaker who was supposed to be here, were grad students together at MIT. And a quick story about him, because he's not here, is that he, which is the best kind of story, is he taught me how to make ice cream with liquid nitrogen. So we used to be in the X-ray lab together, and I think the ingredients were Hydrox cookies, powdered sugar, half and half, and a lot of liquid nitrogen. And you stir vigorously. And then if you've gotten everything basically right, you have dessert. So when he does come, please be sure to ask him to get that recipe. You know, it's like, I go on Epicurious sometimes to make something, and you always get these people who say, well, it called for ketchup, but I put in Worcestershire sauce, and blah, 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 and it tasted like crap, you know. So, and I wonder why. And so you want to get this recipe just right for this ice cream. So I'm going to remind everybody, because I know many people know about this project, of the Event Horizon Telescope, and simply put, we're trying to make an image, as Gary said, of a supermassive black hole. And if we could zoom into the dynamics that this simulation shows here, you'd hope to see strong GR features, and we'd be able to test Einstein's theory of general relativity at the one place where it might break down. And it requires an innovative concept, a push of very long baseline interferometry to the highest frequencies, where global arrays at these frequencies enable you to get the resolution one requires to resolve SgrA star, the 4 million solar mass black hole in the center of our galaxy. I gave a lunch talk today to some SAO people who were visiting, and I likened it to dinosaurs. So we know that dinosaurs probably exist from the fossil record. We see their footprints, we see their bones. We've never seen one. Imagine if you could take a picture of a dinosaur. Imagine if you could take a movie of a real dinosaur. So we're trying to see the unseen, and we're building a telescope to do that. So I want to call attention to the team here. I mean, there are almost, I think, 100 people working on this project around the world. The team here is very, very special. We've built up a very capable group that specializes in digital signal processing, which, as I'll explain to you, is really the lifeblood of what we're doing, as well as a lot of dedicated people, postdocs, graduate students, engineers, faculty. So it's quite a group. So I start by showing you Centaurus A. This is 3 megaparsecs away. It's an active galactic nuclei with dust lanes going back and forth. And of course, in the radio, you get this iconic picture, which, by the way, got me interested in astronomy. I know everybody must have their own iconic image that hooked them on the field. And I will unabashedly say that when I saw this, it really did knock my socks off. And my socks were pretty tightly on, so it was a big knock. And you see that the kind of energy that's required here is about 10 to the 19th hydrogen bombs. And your mileage may vary. How big is a hydrogen bomb? Who really cares? But it's a lot of megatons. And of course, you can't get something like that amount of energy funneled out into these north and south jets, so it has to be a spinning black hole. The only way really to get that kind of energy liberation is through liberation of potential energy through gravitational accretion onto something that's so small you can start to approach to near the event horizon, and you liberate about 40% of the rest mass. So we're trying to find out what's happening in there, and if we could resolve that area, we could ask questions and hope to answer them that are really fundamental in astronomy and physics. Is there an event horizon? Does GR break down, at this special laboratory of extremes? How does matter accrete and outflow near a black hole? Do they have spin? How do they launch jets? One might even hope to look at the quantum nature of black holes. We typically think of them as classical objects, but maybe there's some kind of observable that could link to quantum states inside. So I want to start by showing you what we would see if we had infinite resolution goggles. We'd see something like this, a shadow cast by the black hole itself, by the strong gravity of the black hole near the event horizon. And this was shown early on by Bardeen in 1973. And at the time, he said something interesting, and this was called to my attention by Michael Johnson, the postdoc in our group. And Bardeen said, it's important to get this shape right. It probably will have no use later on, because we'll never be able to resolve that. We'll never be able to see it, right? How many quotes do we know like that in physics? Like this is very interesting, whatever. And this image here, which I'll show you as the last slide in my talk, was simulated by Jean-Paul Luminet. I love that name, by the way, who asked himself, what would a thin accretion disk look like around a supermassive black hole? And of course, you're seeing the back of the accretion flow here. And if you look at if you want to ask the size of this shadow and the shape of it, it's determined completely by Einstein's field equations. And if A is 0, the black hole is not spinning. It's about the square root of 27 times the Schwarzschild radius. And if it is spinning, it's about 9/2 across. Although if it's spinning, then of course the shadow is somewhat asymmetric. But it's still 9/2 across there. And the shadow and the shape encodes GR, and through work by our colleagues in the University of Arizona and elsewhere, we know that if we could image this shadow, we would be able to test Einstein's theories. So that's one of the things that we are focused on with the Event Horizon Telescope. And this holds true no matter how you light up three-dimensionally the space-time around the black hole. If you have Keplerian motion, spinning, or Bondi accretion, or there's a schematic model or a full fluid GR MHD model, you still wind up seeing this shadow feature, which is effectively the last photon orbit. It's the last place where photons can fully concentrically orbit the black hole. Now, that's what light does. Matter also is constrained to do some very interesting things close to the event horizon. Around the Earth, you can have circular orbits at any radii, but around any radius, but around a black hole, of course, you start approaching the speed of light, and then very odd things happen. So if you are orbiting a black hole that's not spinning, you can get within 6 Schwarzschild radii before you pass through what's called the innermost stable circular orbit, and you have to spiral in to the event horizon. If you're orbiting opposite to the rotation of the black hole, then you can extend that innermost stable circular orbit to 9 Schwarzschild radii. And if you're prograde, if you're orbiting with the spin of the black hole, you can cinch up to within 1 Schwarzschild radii. Now, I love this particular diagram. It was in Sky and Telescope. What's not to love? But there's an order of magnitude difference here. So with strong GR effects evident near the event horizon, we may hope to observe these particularly, or at least model our data, taking these things into account. So let's get right to it. What are we observing? The best case for a supermassive black hole, or really a black hole of any mass, is SgrA star, this dot here, in the center of the Milky Way. You see tendrils of ionized streaming gas into the center here. And when you look closer in, with infrared telescopes, you wind up seeing this incredible dance of stars around here. I'm sure everyone has seen this by now, and it's extraordinary work. I mean, having some unseen mass here toss stars around like planets is really extraordinary. The central mass has to be about 4 million solar masses, and the shadow diameter associated with that is 50 microarc seconds. And that will be important later. So let's just keep that in mind, because that's effectively the magnification or angular resolution that we need to get with a very long baseline interferometric array. And there's so many fruit analogies here. I was just in Hawaii, so maybe it's a rambutan on the moon, or an apple banana, or something like that. But I've also heard that it's equivalent to reading the date on a quarter held up by your friend in Los Angeles if you're in New York, something like that. I think it's about equivalent. So we see these amazing orbits, courtesy of the German group and UCLA group with Keck and the VLT. But you also see light curves that tell us that there has to be something very small in SgrA stars. So this is a background star that's used for astrometry in the infrared studies. And SgrA star has a lot of bumps and wiggles here. And through light crossing arguments, you derive a size scale of tens of Schwarzschild radii. The same thing happens in the X-ray. You get very sharp flares. And just the time differential between these levels tells you that you're looking at something on the order of a few times 10 Schwarzschild radii. So it's very massive and it's very small. It's the best candidate we have for a supermassive black hole. And it also, luckily, peaks in the spectrum. So we're looking primarily at synchrotron emission. You can get these arguments that go like equipartition between the kinetic energy of the particles and the condensed magnetic field, and you wind up getting a synchrotron spectrum here that's self-absorbed in the radio and then turns over, becomes optically thin. And the sweet spot really is in the millimeter and submillimeter. And that's thankfully where we can get the kind of resolutions we need using high-frequency telescopes at the edges of the global disk. So why is this VLBI different from all other VLBIs? I don't want to get Talmudic on you there, but that's really the question. I didn't plan that at all. I just why is this? So this is well, yeah, it's a little early for that. So this is I love showing this diagram because this is an ancient diagram, and it shows magnetic tape reel-to-reel recorders on it, right? And it shows a Mark III system. We're already at Mark VI now. But I just like its vintage, and I like it for that reason. But the whole concept here is that unlike an optical dish, where light bounces off, a perfect parabola is focused on the focal plane, you put a camera there, and we phase cohere all the light through geometry. Here we have to record the data faithfully at all the sites around the world with an atomic clock, typically a hydrogen maser, and we timestamp all the data, and then we store it on hard disk, ship it via 747, and there is no faster bandwidth than a 747 loaded with hard drives. And we take it to a correlator, in this case one at MIT. We work very closely with Haystack Observatory on this. And then we phase compare the two data streams that we've gotten, and that gives us a Fourier amplitude on the sky. So essentially what we're doing here, I'm sure most people know this with interferometry, is that we're plucking Fourier components of the brightness with each pair of antennas around the world. Now, at each time. So, and the Earth does turn, so that gives us many, many Fourier components. So when you get to 1 millimeter and 0.8 millimeter on the longest baselines afforded to us by our planet, and we couldn't move to a different planet, but our planet will give us 20 or 30 microarc seconds, so we're able to over-resolve the shadow, and that is where the magic starts to happen. Now going to these high frequencies also lets us peer through the scattering, because the interstellar medium blurs any source towards the galactic center as lambda squared. So even a point source would be all tufty and fluffy. So without even more ado, the reason we're here really is that we did an experiment early on, a few years ago now, in which we had the SMT in Arizona, the Karma array in California, and the JCMT in Hawaii. And of course, we saw all the flux density from SgrA star that we expected on the short baseline here. This is a graph of baseline versus energy received on that baseline. But on the long baselines, where the angular resolution was much finer, we resolved the source. So we're getting much less energy. And this is exactly what you would expect if an interferometer looks at a source of finite size. And we fit a Gaussian to that, and you wind up getting a size of about 4 Schwarzschild radii. So immediately we saw that we're looking at something that is 4 million solar masses in a very small volume. It should be very small from light crossing time arguments. And we're measuring something to be 4 Schwarzschild radii across. So this gets our interest. And this is equivalent to having 4 million suns within the orbit of Mercury. I gave the lunch talk earlier today to the SAO people and the donors, and there were gasps, I think. I'm not sure why they were gasping. I mean, how would you know what that would be like? But I guess they thought that was very impressive. And I think it's very impressive, too. So what do I mean by the scattering? Well, what I'm showing here is wavelength of light and the size that you would expect, the size measured. And this solid line is what you'd expect if SgrA star was a point source. Right? So this, and at longer wavelengths, it really is looking like a point source because you're swamped by the scattering effect. Oops. Hello? Hello? Is this even on?
Yeah.
It is on?
Yeah.
Yeah. But at shorter wavelengths, the intrinsic structure of SgrA star starts to emerge from the scattering. Okay, so the scattering becomes subdominant, and all of a sudden the sizes we're measuring, these red dots here, far exceed the scattering size. So this all builds, by the way, on pioneering work by a whole host of investigators early on that kept chasing this curve down in wavelength. And it was only when we started to get to 3 millimeter wavelengths and then to 1 millimeter wavelengths that we could start to see this point statistically and then very clearly emerging from out of the scattering. So we know that at this point, those 4 Schwarzschild radii that I was telling you about are purely intrinsic structure. There is no scattering that really explains that. So that's Sagittarius A star, and our next best friend for doing this kind of work, for resolving event horizons, is M87, the black hole in Virgo A. You see a wonderful movie here by Craig Walker at the VLBI. So we see there's a relativistic jet coming out, so the black hole is likely to be spinning. We did the same kind of observations and found a size of 5.5 Schwarzschild radii. Now here there is a different interpretation. The interpretation before, by the way, is that, recall that the size of the shadow was supposed to be about 5 Schwarzschild radii. We found something that was 4 Schwarzschild radii. And one of the ways that you interpret that is that as the accretion flow is orbiting the black hole, it's Doppler boosted on one side, so you get a bright patch, and Doppler deboosted on the other side. So you might expect a slightly smaller size if accretion was dominating your emission. Okay, so you basically see the Doppler boosted side of the emission. In M87, the interpretation has to be more nuanced because you know you have some jet with a particular direction here. And a speculative but interesting way to interpret this is to say that we're looking at the innermost stable circular orbit. That magnetic fields are locked into the last orbital radius, they're twisting, and they're ejecting charged particles in this centrifugal whip effect that we think dominates in these kind of low-power jets. And if you do that, you see something very interesting. With Avery Broderick and other theorists, we modeled the apparent ISCO diameter, the apparent size of the ISCO, because remember, it's lensed by gravity, for retrograde orbits and prograde orbits. And one of these curves is if you're looking down on the spin axis, and the other one is if you're looking forward, orthogonal to that spin axis. And we graph that as a function of black hole spin. So the retrograde orbits are just out. And that comes from one of the first view graphs I showed you, which showed that there was a big dynamic range between prograde orbits and retrograde orbits. So if you think you're looking at the ISCO, this rules out retrograde orbits. And this is our measurement here, the blue line. And this is a 1 plus or minus 1 sigma. We may be looking at a black hole spin. It's consistent with a black hole spin of about half the maximal rate. It's a very interesting way to start teasing out fundamental black hole parameters, but you have to use strong GR explanations to get there. So what is in common between this result and the SgrA star result is that we have to use strong GR. It's just not an option not to. So now what's going to happen over the next few years, and where are we going? And I'll tell you, there's been a lot of work over the past couple of years here, which is going to enable all this. But we're increasing the number of stations from 3 to 8. Everything I showed you was for 3 stations. We're going to 8 stations. And of course, the number of baselines is n squared, so we're multiplying by an order of magnitude just the number of Fourier components we may get. It's become very easy with Moore's law to increase our bandwidth by over a factor of 10. That's a rising tide that lifts the sensitivity of the entire array. And we're going to add ALMA, which in a single stroke is going to increase the sensitivity of the array by a factor of 10. And that's also great because SgrA star goes right overhead on ALMA. So we're going to get long baselines. We'll get full closure phase information, be able to model an image, look at magnetic fields, and we'll be able to time resolve dynamics around the black hole as well as jets. So to bring this home, these are the 3 stations that we've used to date. I'll tell you about the efforts at the LMT here, but we brought the LMT online in Mexico. And okay, so unabashed disclaimer. How many of you, raise your hands if you've heard bad things about the LMT? No, don't. Hey, who was that? That was a trick question to identify people to get later. Yeah, so it turns out the LMT has had a rocky road, but I will emphatically say that we have had nothing but extraordinarily good experiences with the LMT. We went down in 2013 to the LMT, and we got 3 millimeter fringes using a crystal. We didn't even use a hydrogen maser. We just schlepped a crystal down there. The next year, we came back with a maser and got 3 millimeter fringes with the VLBA. And the following year, we got 1 millimeter fringes with the Event Horizon Telescope. So the EHT is, the LMT is open for business. We're working on an exciting project to phase up the entire ALMA array, and that is now nearly complete. We have our friends in Europe are readying the Plateau-Dubreuil interferometer in the same way that we're phasing up ALMA, and they also now have very, very good fringes with the IRAM 30 meter. And then, everybody's favorite is the South Pole. Dan Moroney is leading a team down there, which has already put the entire VLBI system down there. So before we had a little sliver of a triangle, and through efforts of people all over the world, really, the team, we now have a really globe-spanning telescope. Oh. And we're also trying to get to Greenland, which you can't see from here. This is what the globe looks like from Sagittarius A star, but the group at Asia A, with collaborators here, are working to take an ALMA prototype dish to Greenland. So a VLBI with the LMT, there it is in extraordinarily nice weather. Here are the first fringes we got with stations of the VLBA. This is Gisela Ortiz, who's a Mexican graduate student who's using a compact mirror here to tune the maser. I questioned this technique, but then the guy who brought the maser with him, is like the maser tech from the company, he provided that mirror. So he was like, this is how we do it. We twist this thing, we look at the mirror. It's standard. It's standard issue, right? Oh, and here's a little factoid for you. You see these light bulbs here? We built a wood sarcophagus that fits over top of this because this is all ambient temperature. So you need a wooden box so that the internal heat of the maser warms the interior. And it stabilizes at about 17 degrees Celsius, which is fine. But at first, we thought it wasn't going to be enough, so we had these light bulbs in there. You turn on the light bulbs, it's like a heating system. So it's very... And plus, you can see what's going on in the light bulbs. The LMT is very important for us because it fills in points in the Fourier plane, shown here in red, that allow us to do some of the imaging that we hope to do. Now, phasing ALMA, this is probably the biggest thing that we've been working on over the past 5 years. It's long been recognized that ALMA is really the gateway to a lot of the Event Horizon Telescope science. And we got an international group together to build a new system. We were one of the first ALMA development projects to phase up all of the telescopes into a single voltage stream that could be recorded on a standard VLBI data acquisition system. And we have done VLBI in this year. This is the status of some of the hardware components. So at the OSF, which is at 9,000 feet, we've racked the optical fiber system, which brings the signals down from ALMA. We now have VLBI recording systems. We designed phasing interface cards, which go into spare slots in the ALMA correlator, which collect all the sum data, format it, and then write it out to these recorders, and we installed a hydrogen maser. So a lot of work has gone into this. It's been a 5-year project. And it's doing very well. So here's an example of the phasing system before it locks up and then after it locks up. It goes from completely kind of random phases here to a mean RMS of 9 degrees. So in band 3, which is 3 millimeters, we're getting phasing efficiencies of about 99%. And that's really a testament to the quality of the engineering at ALMA, but also the fact that we're swimming in signal-to-noise ratio. Right? Even when you look at Sagittarius A star, which is 4 Janskys, you get so much signal that you can phase cohere the entire array on 1-second timescales with SNR to burn. So these kinds of phasing efficiencies are to be expected, and we've acquired them. So what are the results? We got our first VLBI with ALMA to the Apex site. that you think to yourself, well, hold on, that's not any longer than ALMA baseline, but it turns out that APEX had its own maser. So this was truly a VLBI experiment, maser to maser. You can just see the normal, I mean, I'm not going to give you the decoder ring to figure all these out, but these are peaks in delay, delay rate, multiband delay, which show that we're getting a very good cross correlation. And then the pièce de résistance is that we now have 1 millimeter fringes, 1.3 millimeter, from ALMA to the EROM 30 meter. And that's one of the longest baselines that's really possible. It's about 9,700 kilometers. We also, of course, have the band 3 fringes from ALMA to the entire VLBA. So, and we are expecting that by 2017, these capabilities will be available to the entire user community. So anyone will be able to apply for VLBI time with ALMA that leverages the VLBA and make maps with long north to south baselines with high SNR. And then, of course, South Pole. We got lovely fringes on Centaurus A this time between the APEX site and South Pole. So all those sites that I showed you before are well and truly coming online. Now, the other part that I described to you is bandwidth and digital signal processing. The telescopes we use, just by the very nature of the high frequencies, have to be smooth, and they're typically very small. So we lose a lot of signal-to-noise ratio just because we don't have the real estate that longer wavelength VLBI would have. But through an admixture of using field programmable gate arrays and digital recording onto hard disks instead of reel-to-reel tape recorders, we've now tracked a very steady increase in the amount of gigabits per second that we can sustain. We were at tape, went to disk, and now we're on commercial off-the-shelf systems, which are incredibly easy to design, harder to engineer, but very easy to design. They reduce the design time incredibly, and we're following industry trends now, 10, 40 gigabit Ethernet, along with fast digital recording, and that's what's caused the uptick here to an even higher slope. And we hope to get to 64 gigabits per second over the next couple of years. The amount of data we're acquiring, though, will be about 7 petabytes per session, and that's going to put a real strain on the correlation aspect of things. Laura Verticic, a postdoc that recently left us, was really the mastermind behind this new digital back end. We miss her. We wish she were here. But she left us with a very robust design, which we're using now as mission-critical hardware. The progression to 64 gigabits per second, this is kind of what it looks like in the field. We have a kind of a half rack, which takes us to 16 gigabits per second, a full rack to 32, and we need 2 full racks to get to 64 gigabits per second, 4 recorders and ancillary distribution systems and clocks and things like that. And we already have this installed in most places. In a few places, we already have 32 gigabits per second, and then we're going to go on to 64 gigabits per second. The kind of coverage that we hope to get, if you were in Virgo A and you were looking at the Earth, this is the coverage you would wind up getting. And of course, the Earth rotation, as Erwin pointed out, saves us. We wind up filling out a lot of the UV plane, and that makes for interesting possibilities for imaging. So a postdoc, Rusen Liu, who's now at the Max Planck Institute for Radio Astronomy, did a very careful analysis of what we could hope to do. So we're taking a GR model of the jet and the shadow around M87 with a full array. We think that we can, with reasonable noise assumptions and reasonable imaging assumptions, capture faithfully many of the characteristics that we want to see here. Without one dish on the continental United States, we lose some fidelity, but we can still see things. ALMA clearly is required, as is the LMT probably. Maybe we can do without Greenland, but all of these sites are very important, but ALMA clearly is the big ticket here. The other interesting thing that you should be asking is, well, that was M87, but what about SgrA star, because there's blurring, and how do you get away from the blurring? And we've made a very interesting advance in that regard. Vincent Fish at Haystack has led this effort. This is a model of what you might see towards SgrA star with the shadow here. And this is what it looks like blurred through the interstellar medium. If you try to image the data you would take in this case, you can faithfully represent a blurred image. But we don't want a blurred image. We want to deconvolve the blurring. And so what we do is we take our visibility data in the Fourier domain and we divide by the kernel of the scattering. So effectively lift up the amplitudes on the long baselines. But of course, they're noisy, so you're also increasing the noise. So it's not perfect, but you wind up being able to buy back some of the shadow real estate that you were missing here. And this is the first iteration of this, and we're working with people at CSAIL, Katie Bowman, I think she's here in the audience, is from CSAIL, and we're working with the MIT group to refine some of these techniques. But we think this is very promising. Now, this is an animation that will be familiar to many of you here. Avery Broderick and Avi Loeb many years ago asked, what would happen if you had a hot spot orbiting the black hole? And this is going to show you what happens if there's no light bending. This is what's going to show the light bending, and it's going to go from face on to edge on. And the idea here is that these kinds of hot spots that orbit in the accretion flow may explain some of the variations that we see in the infrared, even possibly in the X-rays, but also in the radio. And when Sagittarius A star is active like this, you can't wait for the Earth to rotate in order to make that image. It's like taking opening the shutter and taking the lens cap off when a sprinter runs by. Right? You'll get a blurred image. But we may hope to learn something about the dynamics here through other means, and I'll show you that in a moment. The key thing here is that you wind up seeing asymmetries. So a symmetric blob has multiple light paths around the black hole. So you get secondary images, even tertiary images, when light goes around like 3 times. And you wind up getting the light bent into these wonderful crescent shapes, but clearly symmetric, clearly asymmetric, whereas the blob is symmetric. And then you can ask yourself, well, if this is the model, so the hot spot is here, the hot spot is here, and the hot spot is behind, and this is what it looks like in scattered, can we track that motion as a function of time? And the answer is you can by looking at what's called closure phase. If you look at a closed triangle of stations across the globe, and you add interferometrically the phase in a round trip way, then you get what's called a closure phase, and all of the atmospheric variations disappear. Any phase variations due to clouds or water vapor go away, and you wind up with a clear signal shown here in red that corresponds to this changing model. So as a function of time over 2 hours, you would expect these peaks as the orbiting blob circles the black hole. What I'm showing you here in the black are simulated points of what we would hope to get on the LMT ALMA Arizona baseline and the ALMA Hawaii Arizona baseline. And this is at 4 gigabits per second. And when you go to 64 gigabits per second, which is where we're headed, what I can say here is that I don't know what we're going to see. By the way, that's a disclaimer about all of this. I have no idea what we're going to see with this, right? Which is part of the reason we get up in the morning, right? Because if we knew what we were going to see, it would be engineering. But the reason it's science is because we don't know. But what we can put ourselves in a good position to do is to have high signal-to-noise ratio data. And that is what I am increasingly convinced that we're going to have. We'll get phase variations here through the noise that are so small that they are dwarfed by any kind of real signature that we'd hope to get. So I think we're in a very good position in discovery space. But of course, nature doesn't give us blobs. It gives us things like this. And we have a new postdoc, Hotaka Shiokawa, who's just joined our group, who's looking at GRMHD movies like this and looking at those closure phase signatures, or about to look at those closure phase signatures, with turbulence, seeing if we can pluck out the kind of spectrum of turbulence right around the event horizon through strip chart recordings of closure phase. And the other thing that is quite interesting to us now, in terms of getting new kinds of data, is polarimetry. Everything I've showed you up to this point has been unpolarized light. But of course, there are 4 Stokes parameters. And all the telescopes that we're using now have dual polarization receivers, so we can now, through cross correlation, get all 4 Stokes parameters. And you'd expect to see ordered magnetic fields near the event horizon through shears of Keplerian flows or compressed magnetically arrested disks. Here are some examples from the literature. Sheared fields in Keplerian flows, magnetically arrested disks, still showing some of the strong GR features, but you can now see the ticks of magnetic field here, and even poloidal fields from jets that are being launched from the poles of a spinning black hole. These are some very exciting results, which are these Impress officially? Officially? Yeah. These are officially Impress. This is wonderful data that was really led by Michael Johnson, a postdoc in our group. These are data we took in 2013, but it's taken us quite some time to figure out how to robustly analyze them. And what you're looking at here is, again, a UV plane. So you see east-west baseline length in giga-lambda, and you see north-south baseline in giga-lambda. And at each point here, that's a baseline pair. But in this case, what you're seeing are polarization ticks and fractional polarization. So on the short baselines, you get very little polarization. It's down here in the few, maybe 7% level. But you see it change in direction. Okay, and that's because there are real variations of the polarization angle from Sagittarius A star as a function of time. And we see these in connected element interferometry too. But the real interesting thing is to look here at the long Hawaii to continental US baselines, and you see high degrees of polarization, up to 70%, that change fluidly as a function of time. This is clear indication of a couple of things. One, that there are ordered magnetic fields on the scale of the event horizon, the scale of under 6 Schwarzschild radii. It also tells us that there is a synchrotron, this emission is optically thin if it's synchrotron emission. But this is really a wonderful result because it puts on solid footing decades of theory about how one extracts energy from a black hole. We need magnetic fields to extract that energy, and this is showing us, I think for the first time, that on these scales there are dominant magnetic fields. The last result that I know of that spoke to this was from the magnetar that is bursting close to Sagittarius A star, and people found the magnetic field close to that, but then used models to see what the magnetic field should be close to Sag A star in various accretion flow models. But this is a real measurement on Schwarzschild radius scales. Here's what we hope to do. This is work being led by Andrew Shale, graduate student in our group, who I think is here. Yes, there he is. Andrew is working with Michael, me, and also Ramesh Narayan on ways to use maximum entropy to model and to image the magnetic field. So here's a model with these ticks. Here's what we'll be able to do, or we were able to do last time, so we're still analyzing these data. But next year, we hope to get an array that includes Apex and Chile and so forth. We hope to be able to make these kinds of images with data within the next year. And I think the last thing that I have here is kind of a more speculative but a very interesting future area of investigation, which is looking at the Kerr metric, seeing if we can tell whether Einstein is right, whether the Kerr metric really holds near a spinning black hole. And the way we do this is we violate the no-hair theorem. The quadrupole of a black hole should be expressible purely in terms of its spin and its mass. But if it's not, if you add some other term to the metric, effectively putting a knob on the metric and twist it up and down, then you wind up getting the fact that the location of the ISCO changes. It's not at 6m anymore. It can be 6.5 or 7 depending on the epsilon. And the light bending around the black hole also changes. So if epsilon is 0, if it's a true Kerr metric, then it comes out here. But if epsilon is not 0, you wind up getting these odd light paths, and that changes the shape of the shadow. So if GR is correct, then you wind up seeing something like this. If epsilon is 1, it could be higher. You get compression in the north-south dimension. If epsilon is 0.8, in the east-west dimension. And I'm not sure if we're going to be able to use this parameterization to constrain GR. But what Avery, Broderick, Tim Johansson, Avi, and Dimitrios have done is they've added this epsilon to their modeling. They've taken a radiatively inefficient accretion flow model, which has 3 parameters: accretion, the spin of the black hole, angle of the accretion disk, and then orientation on the sky. And they've added 1 parameter, which is epsilon. And they start to put that into the mix. And what we're seeing is that we get some peak here, maybe it's slightly off 0. This is a 3 sigma contour. So when you graph inclination of the accretion disk and epsilon, you can't really say anything to within 3 sigma at all. What we are hoping, though, is that in the context of these very model-dependent scenarios, we may find up getting islands of preferred epsilon, and that would be very interesting. We can also play the same game with GR-MHD flows, adding epsilon to the ray tracing of those simulations. So this is, at least we have a harness in which to start testing general relativity. So just to recap the roadmap, in 2015, the team was very busy. We got, I don't know what VBLI is. We got something to the South Pole. Dan Maroney will be very surprised. Same thing to the LMT, ALMA, and IRAM. And I want to stress that these are not easy things to do, and it's not a chest-thumping exercise. It's just that it's more of a political exercise. I mean, you try going to ALMA and tell them that you want to rip their thing apart, and it's just not so easy. The same thing with EROM. I mean, they have other things to do, if you know what I mean, and they don't like to see us coming too often. So we're careful, and we underpromise and overdeliver. The Greenland telescope plans are underway. EROM 30 meters is working now, but the Plateau de Bure needs upgrades similar to those that we've engineered at ALMA. The JCMT has a second life now. As you may recall, it was going to close, but now it's open again. It's run by the East Asian Observatory Consortium. The group here is working very hard on the new swarm correlator for the SMA, and that's getting fantastic results. And that has VLBI phasing built into it, and that's been used already. Another group is working on transferring that data to a format that can be ingested by the VLBI correlator called aphids. That's led by a number of people here, Catherine Rosenfeld, Andre Young, and others, and Rurik Premiani. We're planning observations in 2016 that go to 32 gigabits per second, and I think we're on track to get ALMA to join us in 2017. Oh, there we go. So, and again, I want to reinforce that this is a funding salad, and it is a institute salad, but what a delicious salad it is.
What's a good analogy for how it tastes?
Spicy. And again, yeah, so I want to call attention to the EHT team. Here's Casella. One of these is Dan, but when you're at the South Pole, you're just so swaddled that, okay, there's Dan. I point to a random person here. There's Dan. There, right? There's Dan. This is a group photo at the SMA. There's Keiichi Asada from Asia A. There's our own Michael Johnson, Andre Young, Jonathan Weintraub. We're fortunate enough to be funded by the Gordon and Betty Moore Foundation, and there's our program officer who came up to see how the sausage is made. He also thought it was spicy. And this is an operator. Can someone remind me? Sarah. Sarah's one of the operators at the SMA. And then sometimes at the LMT, you're rewarded with a nice view like this. So we have a few minutes left, and I give occasionally public talks. This is public. But I sometimes end with this. This is a B-grade movie about a black hole that's built in a government lab somewhere. So what I'm going to do is I'm going to play this, and then what I normally do is I dissect it a little bit for the crowd, and you guys are going to see immediately what's wrong with this picture. But is there anyone from St. Louis here? There is somebody. I got to be careful what I say then. Okay, next, live in St. Louis. So I hope we'll get sound on this, but here we go.
Another update. It's now been confirmed.
Oh no, we're not getting sound. Is there a way to get sound? Oops.
It's not very loud. You could just hold your mic.
Well, I could hold my mic up there, but is there a way to get sound through the HDMI? No, they're saying no. Okay, so I'm going to hold this down to the speaker here.
Is your volume on the computer?
Is that the equivalent of plug it in?
You're close.
Okay. Well, let's try this anyway.
Another update. It's now been confirmed. Sources at both the Pentagon and the Department of Homeland Security are now officially describing this dark mass we're seeing just outside the downtown area of St. Louis as a black hole.
Now, the best way to describe a black hole is a gravitational field so strong that even light can't escape its grip.
Just straight to the point, since its emergence less than half an hour ago, the hole has consumed everything in its path. It's uprooting trees, it's destroying buildings, it's even been tearing apart several...
Where did this come from?
The bowels of Hollywood. So extraordinary, right? I like the uprooting of trees, because wouldn't trees be sucked down? I mean, but why? How come the buildings are going down, but trees are being uprooted? I think somebody wasn't really editing there. So, or fact checking. So the one thing I focus on is the one you probably all looked at. But so it's eating a building, and I'm assuming that OSHA or building code standards are that a building has to withstand about 10 Gs, right? So if you increase gravity by a factor of 10, the building is going to collapse. And it looked to me, I don't know what you guys saw, but it seemed to me that the black hole was about 25 meters below the surface, kind of moving along, just like plucking things down. So I just said, well, you need 10 Gs at 25 meters. That's a lot. So the black hole mass has to be about 1/10 of a billionth of the mass of the Earth, or about 700 trillion kilograms. You can check me on this, but I'm pretty sure it's right. So the problem, though, is that the event horizon of this black hole, like an asteroid-sized black hole, is 1/trillionth of a meter. So that's like subatomic, right? It's smaller than an atom. And that means that there's just nothing to support it, right? So the black hole is not going to drift along eating St. Louis. It's going to fall, it's going to free fall to the center of the Earth, and then it's going to reach the other side in about, what's it, 20 minutes? What's the free fall time through Earth? 21 minutes. Now, what is antipodal to St. Louis? Wow. It was like, we better figure that out. Like, we got 21 minutes to give them a call, right? Like, we better get on the horn, Like, what is it, Bangalore? What is it, Mozambique?
Not the northern hemisphere.
That's true. So it's the Indian Ocean. So, there's going to be a little tidal wave over there. And then, 20 minutes later, it's going to come back and eat another building. And it's going to go back. So it turns out that St. Louis doesn't get destroyed all at once, right? It happens over some period of time.
The Earth is rotating.
And well, that's very interesting. So I guess it would kind of daisy chain back and forth. Yeah. So yeah, it's going to walk its way across the Earth. I don't know, but it's certainly not going to do what we saw in the movie. So anyway, so I'm going to end as I promised you with this image. This is Jean-Paul Luminet's kind of iconic image that he did really with primitive computers. This is like 79. I'm not sure if he was using a TRS-80 or a Commodore 64. Like, what was he using for this? A wonderful, prescient image. And the best Kip Thorne could do was that, which is pretty close. So it's kind of extraordinary. So we had this early simulation. We had some CGI and modern simulation. And humbly, the Event Horizon Telescope is hoping to see maybe something like this with real data. Thank you very much.
Great talk. But you commit a sin that particularly you should not commit. And that is when you show a video like that, you're just assuming that GR is an accurate description of nature. You have to keep an open mind.
Gravity is only a theory. That's what people tell us.
Okay.
Shep, I take it that basically all of the simulations that you show do not contain any reference to the magnetic fields observed by the magnetar behind. And I take it that the epsilon simulations at the very end might, but do they really? In other words, do those simulations include the effects that you would get if the object had intrinsic magnetic field?
That's a good question. I think that no matter how you light up the space-time, I think the magnetic fields are not going to be affected by the GR ray tracing, but by the metric. I don't understand what you're...
All right. So Stephen Hawking now agrees that the object might not be the technical black hole, but the what he called the metastable quantum-dominated object. In which case, you would have, shown by Leiter and Robertson, you would have surface magnetic fields everywhere, strong, as observed. In other words, they're measured at something like 200 Gauss, and that's about a factor of 1,000,000 stronger than stereo fields. And so that would be your epsilon, would be something like a 200 Gauss field. And the question is, do those models take that kind of a field?
I don't think so. The ones that I showed, I don't think have any magnetic field in them at all. So those predate by many years the new developments.
Thank you.
Although I think it would be very interesting to start taking that into account. We're always in the market for some kind of observable that could be teased out from very careful data analysis of the EHT. So if there is something to be discovered there, I'm all ears. It would be very interesting.
So, carrying on this question, if you were to observe in multiple wavelengths, would you not tease out the magnetic field strength from it?
You could. We hope to do something like that. The problem is at 3 millimeters, the scattering kills you, because the scattering is a lambda squared effect. I'm not done. Were you going to say we should go higher in frequency? Yeah, that's exactly what we're trying to do, right? So you can do some rotation measure analysis in the passband at 1.3 millimeters, but the real ticket is also to phase connect what we would do at 0.87, right? And we do have some of our sites that can go to the higher frequencies, the shorter wavelengths. And that would be a very interesting thing to do, try to nail down the magnetic field that way.
And what kind of interferometer do you have to construct to really look at the magnetar? Field around the magnetar.
Well, remember the magnetar is, how far is the magnetar? Is like 5,000 short-shot radii away. It's very, very far removed from.
It was 2,000 or 3,000
look at
impact
that as
parameter of short-shot radius.
It's 3 arc seconds, so it's a long way.
Yeah, it's very,
Look
very
at
far.
that as an individual source.
Mm-hmm. I'm sorry, to map out the magnetic fields on that. Oh, I'm sorry, the magnetar is not bright enough at the high frequencies for us to see with this array at all, if that's what you're getting at. Maybe Vicky knows. So, the magnetar is, it's been seen up to, I think, 3 millimeters, maybe 1 millimeter, but it's very, very faint, I thought.
Well, it's also likely to be fading. All the magnetars that show radio emission eventually fade out. That one actually has been relatively stable, so
Right.
it's not out of question, but I don't think it's getting any brighter.
Yeah, yeah. I mean, typically pulsars, of course, have a nu to the minus 1.7 or so. Magnetar is a little bit flatter spectrum, but I think I went through this with someone once. As soon as it came on, someone said, "Oh, we've got to look at this with our array." And we ran some numbers. It's a very, very dicey proposition, even with the full sensitivity of the array. What's that?
Even without?
Even with Alma. Well, actually, so Al Wooten looked at it with Alma. I don't think he saw it. So maybe it was too soon, or it wasn't configured correctly. I know Michael Kramer has seen it at Iran. So I think there may be still some hope with Alma this year.
Any other questions? Vicky?
Just the magnetar, my understanding is the rotation measure has been observed to be variable.
Oh, okay, I didn't know that.
Would that, I mean, would that be,
Observable?
that would muddy the waters a little bit?
If we could see it, I think it would muddy the waters. Right? I think we're hopeless in terms of signal-to-noise ratio for that particular object. But maybe I could be surprised.
Well, I guess I meant that that's saying that the environments around it, the magnetic field structure is changing with time. And
I see. Intrinsically, you mean, or is it the interstellar medium that's changing?
well, I think it's dominated at the source, I believe. But,
Yeah. It's interesting. I mean, you know what? We may have some time to look at it. That would be a very interesting thing to do. But I think there's already been VLBI of the magnetar. I mean, Jeff Bauer has done some excellent work with the VLBA. So I think all the real work to be done is with arrays that can look at it at lower frequency where they see it very, very clearly. Because the scattering for the magnetar is just a fraction of what it is for SgrA star. Everyone should know that. The scattering for the magnetar is much different than the scattering for SgrA star, I think. So it's in a slightly different regime.
Steve?
Yeah, is the extragalactic target Centaurus A or Virgo A?
Both.
Oh.
Centaurus A star has a shadow size of about 50 microarc seconds. Virgo A is about 2,000 times more massive, but also 2,000 times farther away, so it's roughly the same. Maybe it's like 8 microarc seconds, the short-shot radius, so about 40 microarc seconds across. Centaurus A is, I think, the shadow size is 5 microarc seconds, so it drops off pretty dramatically. But Virgo A is the main other extragalactic target. But Centaurus A, Centaurus A has a beautiful jet. We have fringes on it already. We're very anxious to go observe that too.
The other thing, if you don't mind, just looking at one of your early diagrams, it looks like you really need a station in New Zealand. And is there
Need or
any
want?
of that?
Oh, you mean
It was
This
the one
guy.
that showed all the baselines, but anyway,
Yeah.
just qualitatively, it looked like that was yeah, there you go.
Yeah, if we had one there. Well, so I talked to Charles Alcock about this once. He's from New Zealand. And so it turns out that the Maori word for New Zealand, when you translate it, means land of the long white cloud. A lot of overcast days in New Zealand. And now Cook, of course, is there, but there's no telescope there. I think there's no high altitude site that's suitable for this work in New Zealand. Similarly in Australia.
Any other questions? If not, let's thank Shep again.